between those predictions, this is the end result that you end up with, which is still a use statistic. Okay? So we end up being able to use those same limiting distributions to not only get the confidence intervals, but also to be able to do the hypothesis testing. So there's another sort of small subtlety to this, which is that when we do something like confidence intervals, we might be interested in looking at a particular point. Right? Want to say, I want to know if I predict here again, how different might the prediction be? When we do a hypothesis test, something set up like this, typically what we want to say is not are these features relevant at this particular point, but are they relevant anywhere? Right? Is there anywhere in the feature space where these make a difference? So typically we want to do this at a bunch of test points. So I'll denote this by capital M. And then the end result of this is that we'll end up looking at the squared differences between those two versions of the ensemble predictions. So this is what the final version of that test statistic looks like. Something that's chi-squared capital N, where capital N is the number of points where. Okay, so testing for additivity, I'll probably go through a bit more quickly. We have two notions of additivity, what we call total additivity and partial additivity. So total additivity is what I had shown on the initial slide, and this is, I think, what scientists typically think of as being additivity. So if I break these into two groups, again, x1 and x2, can I just write it as a function of the features that are in x1 plus a function of the features that are in x2? Okay. And at partial additivity, we'll say, okay, now suppose we have three groups, x1, x2, and x3. And maybe I don't care about what happens between x1 and x3 and between x2 and x3. I just want to know if x1 is additive with respect to x2. Okay, so I just want to know, is there an interaction between x1 and x2? And so we end up writing this like this. Can I write this as a function of x1 and x3 plus a function of x2 and x3? So again, in this context, in partial additivity, this would mean I can change the levels of x2 without affecting how x1 affects the response, but I don't know how x3 works into that. Okay. All right, so the way that we think about doing this, again, I'll just sort of talk through this quickly because it's not as straightforward to go over, but what we can think about is saying, actually, let me just skip the next slide here. So again, suppose that we just have two features, x1 and x2. So here's our feature space, and now we have our response service up here above. And we'll say, okay, let's just define a bunch of levels of x1 and a bunch of levels of x2. So we end up with this grid-like structure. Okay? So if x1 and x2, if these features were categorical, if they were categorical variables where you sort of naturally have these things broken out into different levels, then this makes sense. If they're continuous, then you just sort of define this as you see fit as the experiment. But in any case, you end up with this sort of grid structure, and you end up treating this essentially as factor levels in an ANOVA setup, and so you can rely on that same sort of theory to get the same sort of hypothesis test that you're used to doing here. So if you haven't seen that sort of thing, this is probably going to be a bit foreign, but the idea is, in this example where we have this sort of natural test for total additivity, we can rewrite the null hypothesis like this. So if you've ever had a course in linear models or design of experiments or anything like that, we have this dot notation here, which sort of means we're defining these effects as sort of being in terms of the overall mean. But we end up being able to write this equivalently in this form, and we can sort of estimate empirical analogs of this, and we play around a little bit with some multiplying by a matrix out front. And the end result of this is that we end up being in essentially the same context that we were when we tested for significance. Okay? The difference being that when we were doing tests for significance, we might just pick points sort of randomly throughout the feature space where we want to test. And here we actually put some kind of structure on what we want to test. So we define this grid structure. Okay. Okay, so one more sort of small theoretical thing before we get into the more exciting stuff. So as I was sort of hinting at going through here, typically you want to apply these tests at as large a grid or as many points as you can, right? Those are essentially the questions that you want to answer, and to answer them best, you want to do them at as many points as you can. The issue with that is that the more points we have, the larger those variance or covariance parameters, the more difficult they are to estimate. Okay, so when we start testing at a bunch of points, those variance estimators, or sorry, those variance parameters become covariance parameters, and the more points we use, the larger that covariance matrix parameter is, And so to get around this, we're sort of borrowing from some really, really recent developments in what are called random projections. And so just to give you sort of an intuitive feel for this, the idea is that we have a bunch of points where we want to do these hypothesis tests. And so what we'll do is we'll say, well, we're going to project down onto a lower dimensional space randomly. Okay? And the advantage to that is that we project down onto a small enough subspace where we can do all of these hypothesis tests, where we can get these test statistics pretty easily. Okay? So if we only did this once, this would be a bit of a problem because you're throwing away a bunch of data in doing this. So the idea is that we'll do this a bunch of times for a bunch of different random projections. And then each time we do that, we'll repeat the hypothesis test. So we'll get a bunch of test statistics and a bunch of p-values. And then the final test statistic that we'll end up using is actually the average over all of those p-values from those tests. So there's a lot more sort of behind the scenes here, but does that give sort of an intuitive feel for the goal? Okay. All right, on to the fun stuff. So eBird is it's a very, very big project at the Lab of Ornithology at Cornell. And the basic idea is that about 5 to 7 years ago, the ornithologists at Cornell got together and decided it would be really good if we set up some kind of website where people could log in and submit reports of bird observations. Okay, so people log in and they say, I was at this place at this time and I saw this many of this species of birds. Okay, and the point of this was then that Cornell was going to take all of this data and aggregate it and get some idea of where birds are at any given point of the year. So get ideas of abundance and also migration patterns. Okay. This grew really, really quickly, a lot quicker than I think anyone at Cornell anticipated. So as of now, about 5 years later, there's over 100 million observations that have been submitted and over 1,000 features that they're using to actually make those predictions. So the first features that you might think of are sort of the obvious ones. It's the location, the time of day, things like this, things that the person who made the observation can easily report. But now they have access to a bunch of more databases, which allows them to get what they call GIS covariates, which are things like, given a particular location, what's the kind of land cover in the area, how close am I to the nearest major body of water, these sorts of things, and also information about the weather. Right? So they want to eventually be able to do this on such a fine scale so as to say, you're in this place at this time, what was the weather like and how is that going to impact how the birds were reacting in that given area. Okay, so there was originally a bunch of different goals, which I'll sort of let you read through if you like, but really the main purpose of this was to get ideas of abundance in different areas of the country and also to look at migration patterns over the course of the year. Okay. So as you might expect, this is a pretty difficult problem. 100 million observations is a lot to try and make sense of, especially when you have 1,000 covariates. This is, I think, safely in the realm of big data. This is, of course, big data, right? So besides the problem with the data itself, there is also this more subtle problem, which we brought up to them, which was an issue of the birder density themselves. So the people that make these bird observations are called birders. And this was something that I had brought up to them a while ago, and they were saying, oh, yeah, maybe it's important, maybe we'll try and take it into account. So this slide I mostly just have in here for comic relief, but is there anyone who can guess what this is? What this is an image of?
The joint distribution of birders.
Close. You don't need to feel bad. No one's ever guessed this right. This is a kernel density estimate of the birder density in New York. So up here, up along the back here, this is sort of the Canadian border. Then you come down here along Pennsylvania. This is New York City. This giant peak in the middle, where there are overwhelmingly more people submitting observations than anywhere else in New York State. Anyone want to guess what that corresponds to?
Central Park.
It's the Lab of Ornithology. Yeah. So it turns out that the people that work on this project really like to submit data to this project. And so this, when we started working with them, this was sort of one of the first things that we talked about was we need to take this into account because this is a big problem. Unless you're going to try to make the argument that there's 4 or 5 times as many people in Ithaca as there are in New York City. Okay, so let's hope this works. So this is one of the migration maps that came up out of this. So they've done this for hundreds and hundreds of different species. This is for indigo bunting, so this progress bar here is tracing out over the course of the year. So we're getting into winter, end of the year, coming back, still winter, and you'll see once it gets into spring, we'll see them start to come up. So here we see them starting to come up. They're going back down. But the basic idea is that you sort of see what's going on, and you can actually trace out some pretty fine features along here if you zoom in and look at these predictions closely enough. The one thing I wanted to point out, though, is that if you look over in this general area, at some point you can see that there are not birds there, but you will at some point see. Did anyone see it? Okay, there is an area here in Southern California which has a particularly large number of birders. There's one thing what I like this example is that you can actually see the effects in some cities where there just are a lot of birders. So if one person said I saw it, or maybe I should say 5%. Sure. One more time. Prove I'm not lying. You saw it. This is actually pretty good, though. I mean, it was a lot of work to get these things down to where that was a reasonably negligible effect.
So is it just that those people are confused?
Yeah, well, there's a lot of subtle problems with this, which is that if you, like with birder density, there's nothing to take into account if 10 people see the same bird. Because on the back end, it looks like over 10 birds there. Must be a whole. And, if there were 100 people in the park that all saw the same bird, these sorts of things are difficult to take into account. The other thing that's actually interesting is that over the course of the year, the weather in one area of the country might be really, really similar to the area in a different area of the country at a different time of the year. And so the weather might be so similar that when you try and predict these things, it's like, oh, they're always there when the weather is like this, so they're probably over here. It was, not with this species, but with other species, we were getting, when birds were sort of migrating south to Louisiana, like in the fall, you were seeing them in the dead of summer, like in Wisconsin. So you'd sort of see like, this big like sort of flare up here, and then also a giant flare up here, which obviously was not really going on. But yeah, it's a difficult data set to try and analyze. And also another problem with this is that there's no sort of guarantees that people are actually seeing the birds that they're saying that they're seeing. So, right? So a lot of people are saying, oh, I was here and I saw this.